Is there any volunteer in the room? So M3 Collapse. So this is the Singapore set, right? So do we have any volunteer? So John, do you have the video, right? So if there and we don't have the volunteer to help to play the video, then you play the video, okay?
Okay.
Okay, so let's start. So Hui, are you ready? So we can start.
Yes.
Okay, so yeah, welcome to this challenge session. So the challenge name is Intelligent Cockpit Speech Recognition Challenge. I'm Lei Xie from Northwestern Polytechnic University. I'm very happy to chair this challenge session. So this is a joint event co-organized by many organizations, including Northwestern Polytechnic University, Tianjin University, Nanyang Technology University, ASL, WeNet Open Source Community, and Li-R2. So actually, we know that the cockpit speech recognition is a very hot topic right now. And generously, ASL provides the data to this challenge. Okay, so let's invite the CEO of ASL, Bu Hui, to announce the results and the awards. Okay.
Yes.
So
Okay.
Yes. I show the slides. Okay.
Okay. Thanks, Assistant Chair. Hi, everyone. It is my great honor to present this award. Now, we have two track of the challenge. Now, the challenge result of the limit model size track, just the track one, summarized in this form. We only show top 10 teams in track one. So the third place team is track one, is T9 brief call. The participants come from the University of Sydney. Congratulations.
Okay, congratulations.
Okay, next. The second place team is track one, is T2, FAWA speech. The participants come from China FAW group, Core Limited. Congratulations.
Congratulations to the participants for their wonderful job. Okay.
Okay. Finally, the winner of track one goes to T44 Tune. The organization name is CAP Anonymous. Is requested by the winner team. Congratulations.
Okay, congratulations to all the teams in track one. Okay, we come to the track two.
Okay, here comes the result of track two. We also only show top 10 teams in track two.
Okay. So awards.
So now the third place team in track two is T39 Lee Walls. The participants come from Lenovo Research. Congratulations.
Yeah, congratulations for the Lenovo team.
The second place team in track two is T9 Brew Call. The participants come from the University of Sydney. Congratulations.
Yeah, congrats. So finally, the winner for track two. Yeah.
Finally the winner of track two comes to T40 for the tone team again. The organization name is kept anonymous, requested by the winner team.
Yeah, so this is the secret team, right?
Yes, yes.
Okay.
Okay, congratulations again to all the winning teams. I have finished my speech. Thanks, Assistant Chair. Please go on.
Okay, thank you, Hui, for the announcement, and congratulations to all the winners and all the participants for their wonderful work and contribution to this challenge. Okay, so actually this is a technical challenge session. So we have the following presentation arrangements. So we have actually 4 paper presentation. So firstly, we will invite Zhang Ao to give a brief introduction of this challenge and also summarize the outcome from this challenge. And then we selected 3 top ranking teams to present their work and introduce what they have done in this challenge. Okay, so we come to the first talk from Zhang Ao. Hello, is there any volunteer?
那让他连得进吗？他是以什么进去的？以那个
Hello，
他是以那个就是我们给的account进去的是吗
？Okay, Min Hui, can you hear me?
Yeah.
没有录在，我录在 Cloud 上面吧，应该是。
Who's?
Is there any volunteer in the Singapore side?
有点奇怪，因为都显示在录，为什么只我显示在我的录呢
So who is playing the video?
It's like the volunteers in the video, in the audio, and my video is.
Actually, this is not the new video. I think it's this old one.
Yes.
那这我退出，他是不是就
maybe Zhang, you can play the video from your side, okay? And remember to share the sound at the same time.
University, Nanyang Technological University, Beijing Shasha Technical Committee, and Leo.
Hello?
Recording stopped.
Can you see my video?
Hello, is there any volunteer?
Okay, can you see my video now?
Yeah, we can see your screen. Yeah, you can play the video. Yeah.
Okay.
The sound is very small. The volume is very small. So you can raise the volume.
It's better now?
It's not so good. So you raise your volume, yeah, and also share the sound from inside. So you can share your screen and remember to share the sound at the same time. You can try again, yeah.
That's that track and baseline.
Much better now, yeah. Go ahead, yeah.
Hi everyone, I'm Ao Zhang from Northern
Recording in progress.
This is introduction of the paper title of the ICSRC 2022 Intelligent Cockpit Recognition Challenge. That set checks baseline results. This is a joint work of Tinding University, Nanyang Technological University, Beijing Shashell Technical Company, Winner Open Source Committee, and Li Auto Company. In this presentation, we will introduce our research motivation firstly, and then we will describe our challenge dataset, track, and baselines. Finally, we will make a summary on both tracks. With switch intention become an important human high-code interaction method, intelligent coping speech recognition has become one of the most valuable challenging tasks of speech technologies. But intelligent coping speech recognition faces many challenges in acoustic and linguistic. For acoustic, the acoustic environment of the cockpit is complex because cockpit has special reverberation and there are various kinds of noise during driving, from both inside and outside. For linguistic, the main content of intelligent coping speech recognition contains many named entities, which is real input data and hard to recognize. Besides, the shortage of public data and the lack of combo testbed limit relevant research. In this presentation, we will review the challenging setup and summarize the challenging outputs and discuss major techniques and tricks used by some new systems, which will promote relative research. In this challenge, train set is consisted of open source data on the OpenICSRC, which is listed in the table. The UL test set is collected in the new energy vehicle with a hi-fi microphone placed on the display screen of the car. In terms of acoustic, the data covers most of the common cockpit acoustic sequences. And in terms of linguistic, the data can be divided into 5 categories, covering the common contents of intelligent cockpit speech recognition. The distribution of data is shown in Figure 1, and we can view the acoustic environment of cockpit from the sample. This one is clean.
帮我声音稍微调大一点。
This one is noise.
帮我小点声。
For the track setup, consider the actual intelligent coping speech recognition application. The demand for systems is twofold. With better internet connection, one can run on the cloud side with a larger model and higher performance. Another one is designed to run locally on the vehicle with smaller footprint, lower latency, and whereas better privacy. Therefore, we simply set up 2 tracks in the challenge in terms of limitation on the model size. We employ standard character error rate as an evaluation metric. We release baseline recipes based on the WinNet toolkit for quick start and reproducible research. Specifically, our baseline SR system for the standard configuration of conformer with a 12-block encoder and a 6-block decoder. The dimension of attention is set to 256 and 2048, and our attention head is set to 4. As for the acoustic feature, we use 80-dimensional Milford bands, and the whole network is trained on HL1. The training object is the combination of the CDC and the attention objectives. For inference, we adopt the attention rescoring and decoding strategy as default. We also apply spec org for all data during training. Now we summarize the challenge results. Totally 25 teams finally submitted their systems and the CERs for the top 4 teams in summaries. Observing the detailed performance by subsets of different categories, we can see that the phone call and the POI subset, which involve context and location addressing, are still challenging for a general speech recognizer with the current limited training data. Specifically, there are clear performance gaps between the air conditioner subset, which is mostly composed of face control commands, and the other subsets, which are much richer in linguistic content. We notice that the winner goes to T044 in both tracks with the lowest CER, surpassing the official baseline with a large margin. Next, we'll summarize the technical in terms of network structure, data compilation, training strategy, and language model. For network structure, we can see that most teams adopt the transformer-based encoder-decoder model. Specifically, the conformer architecture is mostly employed as the encoder. Considering the low size limitation in track 1, most teams try to adopt fewer network layers or smaller header size. Note that the team 044 even balances the decoder and only keeps the encoder with CC as a cookie model. In track 2, without limitation on model size, when the team T044 employs an extremely large model, which exceeds the model size of other teams arbitrarily to bring greater modeling ability. Other teams also make structural improvements. For example, Team T039 adds a predictor and anti-loss to the transform-based model and the integrated model, which leads to 0.48% of soil CI reduction compared to the original model. They also tried the recently proposed switch former. T009 adopts a self-conditioned folder encoder and the intensity loss to perform an interactive refinement reparency by setting a multi-shared encoder layer with fewer parameters, which leads to 6.49% relative CI reduction on the test set. Since the critical environment of the cockpit is complex, reflected from the released data, data augment is adopted by most teams to achieve better data coverage. Noise and reverberation augment is widely used. Moreover, most teams adopt speed perception spec aug to further algorithm augment. Team T099 uses the provided data to train a TTS model, particularly for cross-user in-short speech for more no training, with a recent advance in speech generation. TTS-based data augment has gradually become a prominent solution for SR into trained data security. Speech enhancement is granted by Team T039, with the DCRN is adopted to remove noise from the released clean speech. Due to the linguistic challenges of speech recognition, many teams choose to first use end-to-end models and language models to improve performance. N-gram is preferred in track E for 1 limit for the limit of model size, while N-language models are commonly used in track 2. Graph point to control the model size in track 1. Many teams have adopted special tricks to achieve of the universal speech recognition. For example, Team 042 used depth fielding on trained data to reduce the model size and bias the model. And T009 used the n-gram and transform score in the decoding. The winner team T044 built a 6-gram language model for both tracks with significant iterative strategies which bring substantial performance gain. Their methods can be divided into 3 steps. Firstly, a 6-gram language model is trained on the transcript of the training set to eliminate the domain mismatch between the general training set and the released evil set. We select the uncoded n-gram graph from the evil set based on the well-trained 6-gram language model. Secondly, randomly replace the original phrase in the training script with the selected uncoded phrase according to their part of speech, and simulate more data in domain. Finally, a new language model is trained based on the simulated data and compared with the well-trained language model. We repeat this stage multiple times until there is no uncoded phrase in the evil set. In order to better explore the potential of the end-to-end models, several teams study some special training strategies. Particularly, Team T002 employs a curriculum learning strategy to the training data ordered by noise condition in terms of the SNR. It turns out that the SR model can achieve better performance when provided with a better organized training data. For example, the one here containing of training samples that exhibit a discriminating SNR level. In other words, it is beneficial to learn a model from easy to hard samples. And T009, inspired by the knowledge distribution. The model in track 2 as teacher model and the student model for track 1. Specifically, the track 2 model provides some levels of current ignorance, and they make chaos between the output of the model in track 1 and track 2. This method narrows the gap between the small and large models in the 2 tracks, leading to 30.87% percent relative CER reduction for the system in track 1. We conclude the paper with leading the following major findings. With limited amount of data research system, data augment and sub-retention are relative for Cockpit operating environment. For intelligent Cockpit speech recognition, compromise use several other RF models used by most teams. Large model can bring better modeling ability for both end-to-end model and language model. Abstract language model is an effective solution for the utility challenge. Curriculum learning and knowledge distillation can improve the performance of model. Recognition of named identity is still challenging. Thank you, that's all my presentation. For more details, you can visit our official channel website.
Okay, thank you for the video. And so this is the summary of this challenge. So actually we see a lot of techniques, including from the acoustic modeling and language modeling aspects, and also data augmentation and speech enhancement. So as we know that actually we just provided limited data and also single channel data to this challenge. But in real world that we know in-car environment, actually the acoustic environment is very complicated. So sometimes we need multiple channels. So we know that there may be several microphones embedded in the in-car environment. So we can actually make use of the multiple channel signals. And also there are actually several speakers involved in the in-car speech recognition. For example, we have the driver and we have the passengers and maybe 1, 2, 3 passengers. So actually, sometimes we need to detect who is speaking. So from the passenger and from the driver. So who is the guy that actually talking to the agent, or something like that. Okay, so actually this is a good start point for in-car speech recognition, especially for Mandarin speech. Okay, so let's move on. And actually the second presentation is from the 4 AI ASR system for the ICSRC 2022 Intelligent Cockpit Speech Recognition Challenge. So let the volunteer to play the video. So is there any volunteer can play the video? Okay, thank you. So if you have any questions, so just after the video, you can raise your question.
Today, I'm going to share our solution for the task 1 of the Intelligent Cockpit Speech Recognition Challenge on ICSRC 2022. First, I'm going to show you the overview of our system. As you can see from the figure, there are 2 main parts of our system. One for the training of the model and the other one for the inference of the model. In the training part, the basic structure of our model is CTC AED multitask learning. And the main contribution of our system is the using of a 2-stage training strategy with a frame level alignment objective. In the inference part, a basic CTC WFST beam search decoding framework with a 3-gram language model is used. The code of the training and the inference of our model is from VNet toolkit. Next, I will show the data augmentation methods used during the training of our model. The same as a normally pipeline of ASR data augmentation. The reverberation noise, mixing, spec augmented, speed perturbation, and level masking are used. The difference is that the audio data are generated offline and randomly selected during the training step. The raw, clean audio occupy a percentage of 60. By this method, we can save the training time and help the model to converge faster. Next, I will introduce the detail of our model. For the acoustic model, a conformer AD-based model is used. There are 6 blocks conformer encoder and 4 blocks of transformer decoder. We constructed a different dictionary from the baseline model based on the training and the evaluation data. The total number of model units is 4,259. Different positional encoding methods are used in the two-stage training strategy. For the language model, a 3-gram language model is trained with the KNLM toolkits. The learning rate is set with 0.0032 with 8,000 warm-up steps. 8 NVIDIA V100 GPU are used, and all the code is modified from the V9 toolkits. The CTC WFST beam search decoder are used with the parameters showed in the table. In this page, we will introduce the detail of the two-stage training strategy used in our solution. We modified the basic CTC AD multitask learning structure by adding a frame-level forced alignment objective. The factor of the FA loss is eta, as you can see in the formula. We trained the model with 2 stages, and there are 2 different settings. First is the positional encoding method, and the second is the factor of the 3 objective. For the first stage, an absolutely positional embedding schema is used, and the relative positional embedding is used for the second stage. In this slide, we will show the experimental results. We have done several experiments to investigate the effectiveness of the methods used in our system. Firstly, we use the AirShell and the Magic conversation database to build a development database which is used to train and test the model. We have modified the factor of the 3 objectives, and the experiment results are shown in the table. We found a combination of experiment E4 has the best result. Next, we also investigate the effect of the 2-stage training method. A database is built based on the AirShell database and the vehicle noise background of the evaluation data proposed by the committee of the challenge. And a scenario with FA loss both on the encoder and the decoder has a best result. Finally, the model submitted to the challenge shows a CR of 12.67, and the model says, well. We have two conclusions. First, we used the RFA objective to mitigate the token length gap between the train and the test database. The experiment results show that the method works well. Second, we use the two-stage training strategy to help the size-limited model to converge better and improve the performance on the noisy vehicle database. The result is good. The end. So thanks for listening. If any question.
Okay, thank you for the video. So is the presenter here? Sun Yijia, right? Are you here?
Yes, here.
Okay, so any questions? Any questions? If you have questions, you just unmute yourself and raise a question.
Okay.
So any questions?
I have one
So actually,
question.
Okay. So
I found that you use absolute embedding in the Z1 and the relative percentage embedding in the Z2. Can you tell me the reason why you select the two embedding in the two step? Thank you.
Sorry, I can't hear you clear. Can you repeat?
So you can repeat your question.
I find that in the two-step training, you use the absolute percentage in the first step and the relative in the second step, right?
Yes.
Can you tell me the reason why you set up like this?
Oh, okay. The two-stage training strategy is used to help our system to learn false alignment information. We do this setting to overcome the gap between the training and the test data. And the experiment results show that the conversation data set in the test, we can get more good results.
Okay, I got it. Thank you.
Yeah.
Okay. Thank you. So any further questions from the audience? Okay, so if no questions, let's thank the presenter. Okay, so let's move on to the next presentation. I believe the next one is from the LeVoice, the Lenovo team. Okay, so the name of the paper is LeVoice ASR Systems for the ICSRC 2022 Intelligent Cockpit Speech Recognition Challenge. So let's play the video, and the volunteer can help, right?
Hello,
Okay,
everyone.
good.
It's my pleasure to introduce our paper, The LeVoice ASR Systems for the ICSRC 2022 Intelligent Cockpit Speech Recognition Challenge. In this challenge, there are two tracks set up to allow us for ASR modeling with different restrictions for the size of the model. The accuracy of ASR system is measured by the character error rate. Our paper introduces the system we submitted on track 2. For the training set, we can only use the open source data from OpenSLR with a total of 1,300 hours. The dataset of the challenge contains 20 hours of speech data in total, including the 10-hour development set that can be used for training and the 10-hour test set. Our system consists of 3 modules, including DNS module, TTS module, and ASR module. There are 3 parts of data for ASR training, including original data, TTS generated data, and DNS supervised data. We trained the ASR model with data augmentation, anti-noise, reverberation, and speed perturbation. In the inference stage, we decode the test set with multi-modals and fuse the result of each model to get the final result. In order to suppress noise, we adopt DNS module. We first use the clean data from the ASR1 to mix with the noise to train the base model. Then the background noise in the development set is used to generate a training data set to fine-tune the base model. Finally, the noisy training data is denoised by the base model to obtain enhanced speech. They are used to fine-tune the ASR model. The TTS module generates 2 parts of data. One is clean speech with content of development set and voice of ASR1 dataset. The other is noisy speech with content of training subset and voice of development set. Our proposed RNT AED and CTC AED based 2-pass architectures are shown in this figure. In 2-pass decoding, the 2nd-pass model is often used to improve the initial outputs from 1st-pass models by using N-based reracking. The share encoder is a 12-layer squeeze former. The CTC decoder is a linear layer. It converts the output of the share encoder into CTC activation. The RNT decoder consists of a 2-layer LSTM and a linear layer. It generates hops at each token step. The additional encoder is a 2-layer conformer. It aims to process the output of the share encoder further. The AD decoder consists of a left-to-right attention decoder and a right-to-left attention decoder. The left-to-right attention decoder models an ordered token sequence from left to right to represent past context information. The right-to-left attention decoder models a right-to-left tag sequence to represent future context information. This figure shows the changes in spectrum features after passing to the DNS module. We calculated the SNR of the development set is 0 dB, while the SNR of data through the DNS module is 35 dB. The results of our framework are reported in this table. We also modified the RNT architecture of 2nd generation of Cloudy to support AD rescoring. The best result we submitted is a fusion of 13 best results and achieved 10.2% on the challenge test set and ranked 3rd place among the all submitted system in this challenge. That's all. Thank you.
Okay, thanks for the video. So is a presenter for this team here, representing this team here?
Yes, I'm here.
Okay, Jia Yuan, right?
Yes.
Okay. Okay, so any questions from the audience? So actually, I'm quite interested in the TTS part. So could you actually give us more details about the TTS augmentation? So, for example, the detailed methods of text-to-speech, and also all the synthesized data effective for this task?
Well, TS generated data is used for AI training is normal for us. So we just use the most advanced system which called VITS. So
Okay,
I'm not
end-to-end. Yeah.
Yes, I'm not in charge of this part. So as far as I know, this system need reference audio, right? We see the car noise audio to the system to get the speech in car noise. So that's we thought.
Okay. So actually, you think that adding noise, especially the car noise, is very essential, right? It's very important for the augmented data, right? Yes.
Yes. We think our ASR system is same. Their performance. Data augmentation is important for us in this challenge. So, yes, that's all.
Yes, I know that actually there are many augmentation tricks could be used for data expansion. But I think the text-to-speech data, the synthetic data, actually usually have the different distribution with the real data. So could you tell us, do you have a special consideration on this problem?
Yes, the TTS generated data has a little different with normal data, but we don't have too much car the speech in car noise. So we have to do that. So the TS generated data we need this.
Yeah. So the real data is quite limited. So actually the synthetic data is yes, very useful, right? Yeah. Okay.
Yes.
So if we have a large amount of real data, so actually maybe the contribution from the synthetic data is very small. Yeah. Right.
Yes, I agree.
Yeah. Okay. Thank you. Okay, so if we don't have further questions, so we move on to the next paper. Okay, so the volunteer maybe help to play the video. So the next one actually is the last one, right? So it's the name of this paper is called Effective. Let me check. The paper name.
Hi everyone, my name is
efficient conformer-based CTC model for intelligent cockpit speech recognition. Okay, please go ahead to play the video.
From the University of Sydney. Here I want to introduce the recent development of our papers for the ICSRC 2022. My topic is the efficient conformer-based CTC model for intelligent cockpit speech recognition. And we introduce the reason of our works for automatic speech recognitions in the ICSRC 2022 Intelligent Cockpit Speech Recognition Challenge and provide a detailed explanation. We proposed a combination of intermediate loss regulations for CTC-based speech recognitions with self-conditioned folders, decoders, and deployed with TLG attaches with score-based and acoustic models, which finding a good variety of these techniques provides fundamental accuracy improvements. The third of the models in track 2 decreased by the 38.12% compared to the baseline model. And we achieved a second place in the record period with a third of 9.86%. For the track 1, we apply knowledge distillations to train the teacher-student model unlimitedly, combining the track 1 and track 2 key-loss. The third of the track 1 model drops by 40.18% from the baseline model. And we achieved a third place in the record period with a third of 13.39%. As cloud becomes increasingly important tools in people's daily lives, users demand a safe, comfortable, and more intelligent driving experience, and the concept of intelligent cockpits is gradually emerging. Firstly, the cockpit is a particular acoustic environment with various noise disturbances, including media noise, mid noise, and human voice. It's in a relative closure and small cavity. Secondly, the content of the voice recognition in the intelligent cockpit is mainly commands and phrases, including device control, navigation, and multimedia interaction. It will be many named entities. Therefore, a speech recognition system that is robust and tailored to the characteristic of the digital cockpit is essential to improve the user's intelligent cockpit experience. Based on the already established speech recognition technologies, some mainstream technologies also exist for the intelligent cockpit speech, such as those created by the KLD. It's based on the phenomenon level modular alignment, which converts the sequentials from the acoustic model units to words through the FST decoding networks. Or, for example, the VNet, which directly use the words as modular objects released on the CTC, which is an exact list of the alignment input and output alignment for the sequence alignment. This differs from the traditional HMM word framework alignment approach. We also choose CTC conjunction with attention as decoders for this challenge, and CTC only requires annotation results at the word sentence level, making decoding faster and eliminating the need to generate a mapping of HMM to translation. Our systems was designed primarily for the second phase of the models, shows that our system framework is primarily deformed-based, and for the data augmentations, we use the speech enhancement plus the representation variables speech and TTS, and extract 80-dimensional effects as audio features. We additionally used the two training methods, inter-CTC and self-conditioned CTC, to train the model. In terms of language model for the optimization, we used the scheme of 4-gram plus LM for the limit track model. We used adaptive multi-teacher based on the knowledge deceleration, which can compare the model so that if small models have a big capitalized and compressed, the model have a smaller size. The compressed model is smaller and will be more advantageous with the deployed online. A detailed description of these systems will be explained in the subsequent sections. Then I will introduce the overall framework of our method. The unlimited tracks models and the process shows in the figures. The audio inputs will first process the data augmentations through the CNN model to extract features from the input speech signal. Each layer of the conformers is a complete conformer block. In the decoders, the output of the final layer is mapped to the word list using a layer. The data will be repeated for the decoders n times. Default output is set to the decoders for decoding. The decoder is responsible for the feature sequence of the input speech signal, and the decoder is for conjunction with audio models, the language model, and the lexicon, which will output the worst possible audio to the speech signals with maximum probability as the final regression results. The loss calculated by the shared decoder and the attention mechanisms allow to the model and coverage the add-on optimizer to future optimize and the training model. After obtaining the limit track model as the teacher's model, the compressed the student model is obtained as the limit track model using the knowledge distillation for the language model. In the limit track, 4-gram and the LM models are used with a training text. For the limit track, the language model is the same as the limit track. The only difference is the text used in train, which was reduced by using the pronouns due to the model size constraints. we also do some feature selections in our work. In wave format audio, there is a lot of high frequency signal potentials. However, the factors such as volumes are articulate yet contain more high frequency signal components. A loss of the high frequency signals can potentially lead to the phenomena that do have significant signal peaks, making the off-take models less capable of the model these phenomena. The pre-emphasis is, therefore, the first order high-pass filter, which will increase the energy of the high-frequency components of the signal and acquires more features. This is used by window functions to make this time domain signal seems better suited to the period request of the DFT processor to produce a leakage. We used the DFT to convert the data we see each window from the time domain to the frequency domain signals. The result from the DFT is aptitude about each frequency band. However, humans have different exceptional abilities for different frequency of the speech. Linear with the frequency are for the frequencies below 1 kilohertz, and some audio from the high frequencies are about the 1 kilohertz, and the higher of the frequency, the worse the exceptional abilities will get. So frequency is covered by the male filter back. We select 8 male filter backs, convert the start, middle, and the cutoff frequency of each triangular filters of the male filter to the linear frequency domain. Filter the spectral features after the DFT to obtain 80 filter spec energies. Then perform the log observations. The 80-dimensional filter back is obtained. Next, I will introduce the two training methods for the animate track models. The CTC, intermittent CTC, and self-conditional CTC. Intermittent CTC used the additional constraints to improve the recognition's accuracy effectively, in addition to the traditional CTC loss. The method also calculates the additional CTC loss for the output of the intermittent layer, mapping the output of the intermittent layers to the same lexical domain of the mid layers gives the intermittent predictions. And finally, the intermittent loss is calculated. For the loss boxes of the unlimited models, which is different from the first box, as shown in these figures, the output of the shell recorders is linear transform, and the softmax is obtained by the CTC loss. So L1 is represented by the CTC loss, and L2 is represents the attention loss. L3 represents the self-conditional CTC loss. For the unlimited track model, we use the knowledge deceleration, which is mainly used in the model compression and migration learning to compress the model. We use the constrained unlimited model to decel and then get the compressed small models. It can ensure the recognition effect. Meanwhile, reduce the model size in line with the size limit of the model for the computation and select unlimited track model as teacher's model for training. The compressed model parameters number is 14.82 millibytes, and the FST cell is 24 M.
Hi everyone, my name is Yunshu Chen, also from the Uni of Sydney. Next, I will talk about our experiments and the result. The ablation experiments for the unlimited track are based on the evaluation dataset using 2D CNN to extract features. The acoustic model for the baseline is a conformer-based CTC hybrid model. The language model using 4gram and NNLM, training with 4 text resources. Model encoders contains 15 layers by transformer decoder with dimension of 3, using Atom Optimizer. Learning rate preheading 25,000 steps. The decoder contains 8 heads. The attention dimension is 512. The feed-forward layer is 2048. And the CN module kernel is 15. In our experiments, we compare the difference between different learning rates, replacing the attention rescore, adding the intermediate CTC and different encoder layer as shown in table. In the final model, we choose M6 and achieve a CER of 8.92%. Here, the table shows the result of the limited track experiments on the test set. The CER of the baseline model test set was 53.57%. Our model T1 shows the improvement obtained using the CTC greedy training method, achieving a CER of 17.12%. In T3 to T6, we use the attention rescore, self-attention CTC, inter-CTC training method to train the limited track model. This experiment result have made some progress for the final model. Finally, we use the knowledge distillation to reduce our model size. Compared with using the training model directly, the limited track model was distillation first and result in more stable model convergency and a better final recognition result. Distillation reduced the final parameters to 89.99% of the original and the FST file to 99.94% of the original size. In this work, we combine different training methods in literature to significantly improve the robustness of the speech recognition under the intelligent cockpit. In the unlimited model size track, we successfully combine ETA CTC, self-conditioned CTC, and other training methods. This gives us the best result of 9.86% of the test set, an absolute reduction of 38.12 compared to the baseline model. In the limited model size track, we successfully use knowledge distillation to compress model volume and minimize the loss of recognition accuracy. We believe that if we can extend more training data, optimize our coding method in model training, and improve the loss function calculation method, it's still possible to improve our experiment result further. That's all our presentation. Thank you for listening.
Okay, thank you for the presentation. So the authors of the paper is here, right?
Yes.
Yeah.
Okay, thank you. So actually, thank you for the wonderful work and also the good ranking. And actually, I'm very curious about the knowledge distribution. Yeah, could you tell me more about the details on this? So what kind of distribution method you used? Yeah.
Our checkmark models actually is distilled from the fully trained model with training data. There may be contain some misunderstandings in the figures which show in the presentations before. It was originally intended to express how to get our final result. The test set will itself it does not participate in the model training.
Okay. So any other questions from the audience, from the listeners? Okay, so if we don't have further questions, so let's thanks to the presenter. Okay, so I think this is the last paper of this session. So we just presented the 4 papers. Okay, so as one of the organizer here, I would like to thank all of you to contribute to this session. As I just mentioned, actually the data we released is quite limited. We only have actually 20 hours re-recorded data, but actually we are working on a larger data set. Actually, we are also collaborating with many organizations, especially the ASL. And thanks to Buhui, so we are actually collecting a larger data set, and this data set will be more challenging, and we will have multiple channel signals and covers different scenarios, driving scenarios, and also multi-talkers. Okay, so I think this is we are very quick, right? We only have 1 hour to finish this session. Okay, so thank you all for participating this challenge session, and we have many other events in this ICSRC conference, and hope you stay tuned and enjoy the program we provided. Okay, let's end this session and thank you all. Okay, bye bye.
Thank you.
Thank you, Hui. Bye bye.